Well, then you change the position of this marker. You go to the next one. It's here. Is that right? Hold on. The marker's here. Sorry. The marker's here. And you compare. So here's your first marker of string A, and here's your second marker of string B. So you're comparing string A with B, and say they're not the same. So that's fine. So then you move this marker to the next one. That would be here, and so that would be the beginning of string B plus 1, which would be here, and so on. And so you go with using these markers. So marker here and marker here. So you compare A with B. Don't match. Okay, shift the markers. Now you're comparing A with B plus 1. Don't match. So then you're comparing A with B plus 2, and so on, until you get to the end. And then you shift up A's marker. So you'll shift it from here to here. Okay, so now you're comparing string A plus 1 with no, wait a minute. You got to bring the marker here back to here. So subtleties, right? So when you're shifting, yeah, okay, you can solve that. So when you're shifting you have two markers at any time, right? So when you're shifting your left marker by one position, you have to bring your right marker, because there are only two of them, the second one. So you have to bring your second one, your right marker, back to the end of your new A. I hope you follow that reasoning. Okay. So yeah, I hope that gives you a feel. As I keep saying, there are a lot of details in the design of a Turing machine, and you have to think as a programmer. That's where this long tradition. How long has it been now? This machines, general purpose programmable machines, were mid-40s, more or less. There were special purposes, like the British with their Colossus machine designed by Turing, but that was secret. It was kept secret for a long time. Just a little after the end of the Second World War, the Americans came out with the ENIAC, E-N-I-A-C, which is an acronym, electronic, I'm not quite sure, I'm just guessing, numerical, integrate, I don't know. I don't know. But anyway, ENIAC. And then it started going commercial, and John von Neumann designed his own machine at the Institute of Advanced Studies, and then companies got involved, and when IBM got involved, president of IBM said, I think there's a market for 5 of these machines. And then in the early 80s, machines got personal, integrated circuits. Each person could have your own individual computer, whereas a couple of decades before that, a computer was a huge room, because the technology was based on valves. One electronic valve was about this high, which could manipulate a bit or something, right? So of course, the computers at that time were mammoths. They were huge, and they would break down all the time because the valves would fail. I mean, valves are very hot, right? And they vaporize. The metal vaporizes and fails. So, and we're still on that path. Moore's law. The number of transistors you can cram onto a chip keeps doubling every year, and it's been doing that since Moore noticed the trend, which was in '65. So, in a couple of years we'll be at 2015. So that's 50 years, half a century of Moore's law. That's a lot of doublings, right? With an 18-month or more or less doubling time, that's a lot of doublings. So today's chips contain tens of billions of transistors. Okay, so it's largely Moore's law that is generating the massive problem that humanity will have to face this century of its own supersession. Humanity will be superseded by more intelligent creatures. We as human beings, as a species, we will no longer be the dominant species. And that issue, I'm predicting personally, will be such a hot potato, generates such passion that a major war is coming and killing, with 21st century weaponry, that war will kill billions of people because there's such passion involved. We're talking about the survival not of a country as in 20th century wars. This time we're talking about the survival of the species. That will be our dominant 21st century issue. Now, because I'm mid-60s, thank God I will not see it. I will not have to live through this horror. But if you're young, very young, you will. I have a grandson. He will see it. And if I'm correct in terms of the numbers of casualties, in a major war over species dominance, human beings fighting for the ideal that human beings remain the dominant species, not being taken over by a superior species. And the other side, effectively, their dream is to create godlike creatures, like the next phase of evolution, with capacities, mental capacities, trillions of times above the human level. And the big picture, there's a whole universe out there, and probably advanced civilizations, billions of years older than ours, that have moved on already billions of years ago. So there's a whole world of phenomena out there, way beyond what human beings can even imagine. So godlike. So the ideologies on both sides: one, preservation of the dominance of the human species, and the other, building gods. So two very powerful, utterly opposed ideologies, and hence inevitable conflict. So I'm to write an essay for a book just on this. So I talk about the inevitable Artelect war. Artelect is the label I give to these godlike machines, artificial intellect, that's where the word came from. And the Artelect war is this war over species dominance. And the people who want to build these machines label them cosmists, based on the word cosmos, because that's their perspective, the big picture. And the other group who want human beings to remain dominant species call them Terrans, Terra, the Earth, because that's their perspective, very, very small-minded, pathetic little human lives snuffed out in 80 years in a universe. That's the big picture, in a universe with trillions of stars that's billions of years old. So the cosmos will look on the Terrans as very little people, and the Terrans will label the cosmos monsters because they're prepared to take the risk that human beings, billions of them, get wiped out. So who's to say if these Artelects may eventually become so superior to human beings they may look on us as a pest and just wipe us out easily because they're so superior to us, the way we humans wipe out chickens. We don't care about them, we just eat them. Right? Who knows? So anyway, that's okay. Get onto that sort of stuff. I lose my track of thought. Where were we? Right. Yeah. So we're talking about top-down design. You get it step by step. We went from the global strategy to then strategy of shifting markers, marked symbols, so that A could compare with A plus 1, A could compare with A plus 2, and so on. And you're shifting the markers in such a way that you systematically scan through all possibilities. All right. Now, some more comments. This technique that we've just been using, of using marked symbols, what does that mean? Well, here, I'll just explain it. We were suggesting replace the hash. You have two marked symbols in your string, or your string of strings. Right? Two of those hash symbols will be marked, modified, changed. And so you could have another symbol in your tape alphabet, hash dot. You see a little dot here, okay? And now you can have anything. You can have any other symbol, but so choosing it to be this way, you have a symbol that just looks like hash dot. That means, that reminds you that what it was before you dotted it, before you modified it, before you marked it, that it was a hash symbol. Okay? Now you can dot any symbol, but if you do that, you're going to have to add this symbol, the dotted symbol, whatever it is, the dot of something, of some symbol. You have to add that extra symbol into your tape alphabet. Okay, right? So now to go the other way, when you